Here in the second part of Chapter 9, we're going to look at the critical value approach to hypothesis testing. There's a p-value approach, but there's another way to do this based on what's called a critical value. Now, the critical value is primarily determined by the level of significance. Another way to look at the level of significance is that it's a conditional probability. It's the probability that you're going to reject the null, assuming or given that the null is true. Now, in the third video over Chapter 9, we're going to get into other test statistics, but here we're still dealing with the same test statistic. We're assuming that we know what sigma is, and we're testing the mean. Now, this is the same problem that we used to explain the concept of the p-value. We're going to use this same illustration now to get into the concept of critical values. In this example, our test statistic is a z. That's the standard normal probability distribution. Now, you take the level of significance and you put it into a tail if it's a one-tailed test. If it's a lower tail test, you take alpha, the level of significance, and you put it on the left-hand side, the lower tail. If it's an upper tail test, then you take alpha, the level of significance, and you put it on the right-hand side in the upper tail. The critical value is the point that separates the tail from the rest of it. Now, alpha, another definition for alpha, it's the probability that you're going to reject the null, assuming that the null is true. So alpha represents the probability of rejection. And you're going to put the reject null part in a tail if it's a one-tailed test. But if your alternative has a less than, then put alpha in the lower tail on the left-hand side. If your alternative or your alternate hypothesis is a greater than, then take alpha and put it on the right-hand side in the upper tail. And then we can just go to the z table and figure out what that value is that separates when you're going to reject from when you're not. If you have a lower tail test, you're only going to reject the null if the computed value is less than or equal to that critical value. And for a z, that one's going to be negative. If it's an upper tail test, then you're only going to reject the null if the computed value is greater than or equal to that critical value that you get from the table that's based on alpha. Now, in this particular example, we don't have a one-tailed test. In this particular example, we have a two-tailed test. So there's a different rule for a two-tailed test. Now, the two-tailed test is when the null says equal, and the alternative or the alternate hypothesis, you have the not equal. If it's not equal, it might be smaller than the hypothesized value, but it also might be larger than the hypothesized value. So there are two places where you could reject the null. You could reject the null because the computed value turns out to be much, much smaller, or you can reject the null because the computed value turns out to be much, much larger. 0 is the value that's in the middle. But the basic idea is if you end up in one of the tails, then you're going to reject the null. Now, you want to assign as much probability to rejecting it because it's larger as you do because it's smaller. So what you do is you take alpha and you cut it in half. You take half of alpha and put it in the upper tail on the right-hand side. You take the other half of alpha and put it in the lower tail on the left-hand side. Then you can go to the z table. One of those numbers will be negative, the other one will be positive, but it'll be the same value. Now, the rule about rejecting is basically you reject if you're in a tail. But you reject the null if the computed value is less than or equal to the one on the left side. Or you reject the null if the computed value is greater than or equal to the one on the right side. But you're going to have two critical values if you have a two-tailed test. Now I think the picture makes this much easier to see. The null hypothesis says that the mean is 40,000. The alternate says it's not 40,000. Well, it could be larger, it could be smaller. So to get the critical values, there's going to be two of them because it's a two-tailed test. You take alpha and cut it in half. Half of 0.05 is 0.025. You put that in the upper tail, you put that in the lower tail. Those are the places where you're going to reject the null. If you're in between, you're close enough, you're not going to reject the null. But you have a rejection part in case that sample value is much bigger than what's hypothesized. And you also have a rejection part in case that statistic, that sample value, that X bar value, if it's much smaller than what you're hypothesizing the population mean to be. In this case, when we take the X bar value, the 41,100, and figure out what the Z value is that corresponds to that under the assumption that we know sigma, that it's 4,500, our sample size is 36, and we get the 1.47 value. That's the computed value. Now what I've done is I've drawn a little blue line to show approximately where that number would be on that graph. It's between the negative 1.96 that corresponds to the 0.05 in the lower tail and the positive 1.96 that separates the reject part in the upper tail from the do not reject part. But since it's in between those two, it's clearly in the portion of the graph where we're not going to reject the null. It's not bigger or equal to 1.96. It's not less than or equal to a negative 1.96. That computed value, the 1.47, tells us not to reject the null. Okay, there are a lot of values on this slide. So let's just take this piece at a time. The heading, we have a lower tail test about the population mean. Sigma is known. That information tells you what the test statistic is on the right side. Now you can take that test statistic, you can plug in the numbers for the sample, and you can come up with the computed value. Now down at the bottom on that z-axis, the number that's furthest to the left, it says z is equal to negative 1.46. That number is the computed value. When they plugged the values into the formula, they came up with a negative 1.46. Now if you're doing the p-value approach, you can look up that number inside the z-table. And the probability that you're going to get from the z-table is the probability that you're less than or equal to that point. That is the p-value for a lower tail test. The p-value for a lower tail test is the part to the left of the computed value. But if you looked it up in the table, you would get 0.0721. Now for this particular illustration, right up above the p-value, it shows you that alpha is 10%. You do the comparison between the p-value and alpha. If the p-value is less than or equal to alpha, that's the condition that tells you to reject the null. So in this case, you're going to reject the null. Now if we were doing the critical value approach on this one, we would take the 10% and look that up in the table, and we would find the critical value is a negative 1.28. because the computed value, the negative 1.46, is less than or equal to a negative 1.28, you're still going to reject the null. It doesn't matter whether you use the p-value approach or whether you use the critical value approach. They're both going to give you the same decision in terms of whether you reject the null or whether you don't. Now, we'll flip it over to the other side. Here we have an upper tail test about a population mean where we know sigma. So the test statistic is up at the top. Z is equal to x bar minus mu with the subscript of 0 divided by sigma over the square root of n. Now if you're doing the p-value approach, you would plug the numbers into that formula and you would calculate the test statistic. Now on this slide, that value is to the right down there at the bottom on the z-axis. Z is equal to 2.29. That's the computed value of the test statistic. Now if you go to the z table and you want to find the p-value that corresponds to that one, when you look up the 2.29, you're going to get what's on the other side. You're going to get what's to the left of the 2.29. So you're going to get the 0.989 figure. When you subtract that from 1, then you get the p-value for an upper tail test. You get the 0.011. Now in this particular example, alpha is 4%. But you compare the p-value to alpha. They're both probabilities, so you can compare them directly. The 0.011, the p-value, is smaller than alpha 0.04, and that tells you to reject the null. Now, the level of significance being 0.04, you can go to the table. You're not going to look under 0.04. You're going to look for the value of 0.96. The probability that's smaller is where you're going to get the value in the table. But if you've got 4% above it, you're going to have 96% below it. But to get that critical value, you look in the table for 0.96. Now I don't think there's really a 0.96 in the table, but the closest value to it corresponds to a z-value of 1.75. So you should be able to find that z-value in the z-table. But that's the critical value. Anything that's above that or equal to that, you would reject the null. Because the computed value, 2.29, is greater than or equal to the critical value, 1.75, the critical value approach would tell you to reject the null also. But p-values, critical values, they should give you the same answer. Now on this illustration, we have our test statistic, and we know it's a lower tail test, and we have the level of significance. But we don't have a computed value. This is a point about hypothesis testing. To get a p-value, you have to have the computed value. To get a critical value, you don't. All you need to know is what type of test is it and what's your level of significance. It's a lower tail test, alpha's 10%, so you put that 0.1 on the left-hand side, and then you figure out from the z-table what's the value that's going to separate the reject part from the do not reject part. That's your critical value. So if you go to the z-table and you look up the 0.1 in the body of the table, go out to the margins, you would determine that that critical value is a negative 1.28. But this slide doesn't show you a computed value because this is just showing the critical value approach. What you would do to finish the problem is you could take whatever that computed value is and compare it to the negative 1.28. If the computed value is less than or equal to a negative 1.28, you would reject the null. But you can't make a decision here because you don't know what the computed value is. If the computed value was larger, if it was to the right of a negative 1.28, then you're not going to reject the null. Now we're going to look at one more example of this. We have an upper tail test. We know what sigma is. We're testing the mean, so we have the standard normal for our test statistic. In this problem, the level of significance is 0.05. So the 0.05 is going to be above the critical value. The probability below the critical value, and that's what you need to use the z-table, would be 0.95. So you go to the z-table, you look in the body of it for 0.95. Now this is one of those values that's just right smack dab in the middle. There's a point, let's see, it's 9495, and then there's a 0.9505. The 0.9495 corresponds to a z-value of 1.64, and the 0.9505 corresponds to a z-value of 1.65. So it's exactly halfway, so I want you to go exactly halfway. The z-value would be a 1.645. Now we don't have a computed value. You can figure out what the critical value is without knowing the computed value. But you cannot figure out the p-value unless you know the computed value. The p-value is determined from the computed value. The critical value is determined from the level of significance and what type of test it is. But once we know what the computed value is, if it turns out to be less than 1.645, we're going to be in the do not reject null area, and that'll be our decision. But if the computed value is 1.645 or larger for this upper tail test, then we're going to be in reject part, and that would be the appropriate decision. Now the last two slides in this presentation, in this little video, they show you the general way that you can do a hypothesis test based on the p-value approach. That's what's on this slide. And then the next slide does it based on the critical value approach. Now whether you're doing the p-value approach or whether you're doing the critical value approach, you can do the first three steps. Figure out your null and your alternative. Figure out what that level of significance is. Gather your sample data, calculate whatever statistics you need, and then figure out the value of the test statistic. But you get that computed value of the test statistic. You need that for both of them. Now if you're doing the p-value approach, you just take the computed value of the test statistic and figure out the p-value. If it's a lower tail test, you want the probability to the left of it. If it's an upper tail test, you want the probability to the right of it. If it's a two-tailed test, take those two probabilities, whichever one's smaller, you double it. Now you've got the p-value. You're going to reject the null if that p-value is less than or equal to alpha. Large p-values support the null hypothesis. Small p-values, once they get down to alpha, or if they get below alpha, that level of significance, then you want to go with the alternative hypothesis. But you've proven it if you get a small enough p-value. Now the first three steps are the same if you're doing the critical value approach. Get the null, get the alternate, figure out what alpha is, collect that sample data, calculate whatever statistics you need based on your test statistic, and then plug in the numbers and compute the value of the test statistic. Now you take the level of significance. If it's a lower tail test, you put it on the left-hand side. If it's an upper tail test, you put it on the right-hand side. If it's a two-tailed test, you cut it in half. Put half of it in the upper tail, half of it in the lower tail. But those probabilities determine what your critical values are. The critical value separates when you're going to reject the null from when you're not. But all you have to do is take the value of the test statistic and compare it and make your decision. If it's in one of the reject areas, then you're going to reject the null. If it's in the do not reject area, then that's going to be your decision. All right, in this presentation, you were introduced to the critical value approach. Now, we also went back and kind of reviewed the p-value approach. But you have two ways that you can do a hypothesis test. You can do it based on the p-value. You can do it based on the critical value. Now, when you have a z, either way is fine. But you're going to find out when we get to the next little presentation, the next little video, that when you're doing a t and you're using the table, you can't really do a good job of finding p-values when you're using the t-table. Now, there's a t-distribution that's built into Excel, and the one that's in Excel will do a good job of figuring out what p-values are. So if you use Excel, you can get a good p-value for a t. But if you're using the table, the best you can do is come up with a range. But the next presentation, we're going to look at an example for the different test statistics. We'll have a third example for the z, where you know what sigma is. We're going to do an example where you're testing the mean and you don't know sigma, where you make use of students' t-distribution. And then we'll also look at the case where you have categorical data, where you have qualitative data, and you're testing the proportion.